morning. Today, my lecture is an extension of my previous lecture, that is on the simulation of LTI system, spectral domain properties. So this is the part 2 of that lecture. In this lecture, I have simulated wideband input signal, that is nothing but linear chirp in our case, and I am applying that linear chirp to low pass filter, high pass filter and band pass filter. Okay. Then the energy signal and periodic signal I have applied in my previous lecture, and there I have dealt with low pass filter and high pass filter. Now in this part I am going to show the results of the band pass filter in these both cases. Okay, so let us go to the simulations. So this is what we have. Again, just for completeness. So this is what we have: the input spectrum. This is the input spectrum. Then this is output spectrum, and this is the frequency response of the LTI system or filter. So these are related by the product relation like this, and the power spectral density relations are like this: SY, that is power spectral density, PSD, of output is equal to the input power spectral density weighed by this function, that is square of the magnitude response of the filter. Okay, so this is power, and these are equivalent relations for ESD. Actually, this is ESD and PSD also. Okay, so now these I have already reviewed, and in this one again similar equations. So here we will be more interested in these two relations. Okay, there is one more relation, RXY, RY. So RXY equal to RXX convolved with H of tau. Okay, so there is one relation is not there here. So those three, that is cross correlation, and correspondingly we have the cross power spectral densities. So this is nothing but cross power spectral densities, SYX and SXY. These are cross correlations, and okay. So this is what, these are the expressions which we are going to simulate and prove. So let us consider this. This is the part 2, simulation 5 actually. So this is new signal, that is wideband signal. And here I have to apply first low pass filter. Then if you see the spectrum of this one, this is a chip signal. Starting frequency here the frequency is 0. Okay, so here the frequency increases as the time progresses. So frequency is a function of time. So at this instant, if I take, the frequency is different. At this instant, if I take, the frequency is different. Okay, so it means it is basically linear chip means linear frequency modulation. So this is frequency is increasing from lower to higher. So here in our case, I have started with 0 Hz and ended with 1000 Hz, that is 1 kHz. And I am starting at the left side, that is when t equal to 0. I have the 0 frequency. I am starting from less than 1 Hz. At this point it is exactly 0 frequency, and at the end here, that is at 0.2 seconds, I have the 1000 Hz frequency. Okay, so that is what I have. And this side 0 Hz. So this is what the input signal. Now when I take the spectrum of this one, Fourier spectrum of this signal, I am showing here magnitude spectrum, and this is you can very clearly see that this is it is spanning from 0 to usually up to 800. Actually it is up to 1000, and because of this window effect, because it is not a continuously increasing, and again you are multiplying this signal with gating, and because of that interaction, so you may not be exactly totally see 1000 Hz here, because here the frequency is instantaneous, because as the time changes the frequency change. So these frequencies are called instantaneous frequencies. But when I take the Fourier transform as a whole for the total signal, it considers all the frequencies basically. Okay, so it is a complex phenomena. If you find Fourier transform a bit complex one, but this gives the shape like this. So here in this whatever frequencies are there, instantaneous frequencies here, they are all present here. But as the frequency increases, this decays. Okay, because finally it has to become 0 somewhere. Correct. After this, there is no signal, there is no frequency. So that is how it is approaching. This is the 1000 actually. This is the 1000 Hz. 1000 Hz. So here if you see very clearly the bandwidth of this one. See here the power, significant power is there between between 0 to 600 or 700. So then slowly it is decaying. So basically compared to the previous any spectra, so there were lobes. If you take pulse, you remember I have the main lobe and sinc function basically. So magnitude sinc function, absolute of sinc function. So that used to have a decaying side lobes. Here it is not like that, because here all frequencies are present with equal amplitude. See here the envelope of the input signal is constant. So here you will see some things here. It is because of the because here the frequencies are increasing. At higher frequencies, whatever sampling frequency I use for my simulations, it is because on digital computer I cannot generate any analog signals. Okay, so these are all whatever I am showing. Even though I call it as analog signals, they appear as analog signals because of plotting, because they are joining point to point dots in the waveform. That's why they appear continuous. Otherwise, they are all discrete signals, and especially not only discrete, they are digital signals basically. Okay, so as the frequency, if in the simulations, if the frequency is high, if the sampling frequency must be greater than Nyquist rate. Okay, let us say for example here 1000 I will take. Okay, 1000 Hz is there. So what is the sampling frequency I need? Minimum 2000. So if I take 2000 Hz, I will get 2 samples per cycle. That is during positive cycle 1 cycle if it is a sinusoid, and negative during negative cycle 1 more sample. Okay, so that is what is 2 samples, but it preserves the frequency, but the shape, you cannot see the shape. The time waveform is highly appears distorted. So that's why if you go for oversampling, let us say if it is 1000, if I use 20,000 or 15,000 like that, you will get a smooth curve here. These wrinkles, these zigzag portions, they are because of the lesser but above Nyquist rate only. Okay, otherwise we will get wrong signals. So above Nyquist rate, but they are not oversampled. So if you use oversampling, because at lower side you will see very smooth curves at lower side, because these are all oversampled. Here they are not oversampled; they are just critically sampled. So that is the reason you will get some kind of distortions, but actually they are not distortions. Okay, they are the samples. And if I use oversampling by, as I told you, 15 kilohertz or 20 kilohertz, if I use, every cycle I will get 15 samples, very smooth curves I will get. Then these portions will appear flat. Okay, so that is what is there. Now, coming to the magnitude spectrum of the signal again, they are very broad, and this is the overall, because there's a lot of because I am taking the total waveform. So an instant in, and it basically it is not step frequency also, correct? It is continuously changing. So continuously changing means phase is also changing, frequency changing, and accordingly, because phase is changing, frequency is changing basically. Okay, so phase is first. So because of that continuous change, you will find this kind of complex spectrum. But you can say very wide band spectrum. It is a very wide band compared to any previous signals which we have seen. And let us come to the low pass filter. This you know already, impulse response, and here I have the magnitude response of the filter, low pass filter, and this cutoff frequency somewhere here. This is 0.7. This is a 0.7 point. So I have the cutoff frequency here. It is 100 Hz. At 100 Hz I have the cutoff frequency. But if you see here, there are all frequencies, correct? Even though it is up to 1000, there is 100, everything, all frequencies from 0, 1 Hz, 2 Hz, 3 Hz, like that, every Hz is there in this waveform. So when I filter this with this, so basically what I have to do, y of f equal to h of f multiplied by x of f. Of course, I am considering all absolute values, magnitude spectrum. So this one, what basically effectively what I am doing here is, so this one, this is 100 here, this is 100, and this is, I will continue with 100 like this, and this is something like 100. Okay, so when I multiply this first signal x of f with h of f, I must get this multiplication of the first one and second one is nothing but the third one. That is spectrum of the magnitude spectrum of the output signal basically. So when you see here, this is directly, let me show. Okay, so this portion, whatever I am seeing here, this is multiplied by 1. So again, accordingly, this is okay. So this shape, this whatever below 100 Hz is there, that is all multiplied by 1 here, constant value. So same shape will transfer to the output. Okay, so at this point, but at this point, there is some type increases, a little bit increase, or I think it is after this it will increase. But here, by the time above 100 Hz, at this point it is increasing. But what is unfortunately what is happening is this is pulling down. So this is decreasing, this is increasing. Second oscillations in the spectrum. So this is increasing. Then this increase won't appear here because this is pulling it down after multiplication. So that's why you have one hump like this, and slight pedestal is there here, and slowly again decreasing according to this one. Okay, so this spectrum corresponds to the signal, output signal like this. Okay, excuse me. So here basically this is low pass, this is wide band, I mean many frequencies, and when I convolve these two, see, this is at some convolution, no? So this portion is 0. So because these are all time functions, this is time function and this is also a time function. So I am convolving these two. So most of the time it is 0. Okay, so that 0 will reflect here as in the output here. So the signal is limited up to this, but you can see the difference here. First, here let us say this is the 0 crossing, and this is 0. This is the first 0, and this is the one cycle here approximately. Okay, of course this cycle also, it is not exactly cycle, it is only in approximate sense. So this from here to here, there is some time difference. Okay, this time difference is coming down here. It is here, it has decreased here. Okay, here further it has decreased. So that is because of these frequencies. Okay, because you are convolving these two. Again, it is a complex operation, a linear operation, but complex operation. Convolution means is not straightforward one multiplication. It is a set of multiple products. Okay, sums of multiple products. Okay, so that is what we have. So this, because of this convolution, you will get this kind of waveform. So naturally, this kind of waveform has a little bit higher frequencies compared to this one. I mean, whatever, because of this one. Okay, little bit higher frequencies here. So this is and within the pass band, the frequencies are starting from some lower value. It is increasing. It is going there. This is the DC value actually. Whatever I see is 0.5. It is the DC value. So at this point, I have the DC value is there at this instant. So that is what is reflecting into 0.5 here. Then the frequency is slowly increasing up to 50 Hz. This is 100, correct? So this is 50 Hz. It is increasing to 50 Hz and again it is coming down. So it is something like an oscillator. It is something like an RLC circuit, a resonant circuit, something like that, and slightly added with some additional frequencies. Okay. So basically, I mean, because of this one, this is not a single curve. So this portion, it is something like a narrowband filter, or I mean, it is a narrowband signal, I should say, some kind of oscillator. So that is the reason I am getting this kind of oscillations. Okay, compared to this, these are kind of oscillations. So this is because this has come from the input spectrum. Okay. Now let us come to the RXX, that is autocorrelation function of this one. And if I find the autocorrelation function, it will be having almost something like impulse here. Okay. Then because signal is wideband, so wideband signals in time domain, they have to, I mean, they should appear compressed, correct? So the autocorrelation is like almost like an impulse function. And what about the spectrum of this one? Spectrum is wideband again. If you see here, it is a wideband, and a lot of interactions are there. And here, power is there between 0 to 1000 Hz, and it is not exactly white. That is exactly all values are not blessed with same value. Okay. So this is what is the spectrum. Not much to be explained except that this is a wideband signal. I mean, for this it is wideband. Okay. It is, what is this one? This is nothing but not the spectrum, power spectral density. Okay. So power spectral density, because it is not a periodic signal in our case, correct? So this is, let us say it is one pulse here, one pulse. So it is a single pulse modulated with a linear FM. So in that way, it is an energy signal basically. So that is the reason I have put it here as the energy spectral density psi, not S. It is the power spectral density of psi. Now this is wideband. Of course, there are some values here. It depends on the signal. Okay. So that is what there. Now let us consider the cross correlation. So cross correlation is like this. You can see it is something like a impulse response. It appears like impulse response of a very narrow band filter. It looks like, okay, by experience, by observing several impulse responses, you can conclude that. Okay, so this appears like, for me, this appears like a narrow band oscillations. So I mean, because this frequency is almost same, it is a very narrow band. These frequencies are almost same, around center frequency, very small bandwidth. Okay, that is what it is. So this reflects in this here as a very narrow band, and you have the, I must say that this looks like 100 Hz. This looks like an oscillator, narrowband filter, again like a RLC, resonance circuit, with high Q factor. Okay, so if the Q is high, the bandwidth is very small. Okay, so that is what. So it is like in a second, and it resembles the second order resonator, and yeah, that's why these both shapes are linked. Expression is same, and this is because the dominant frequency is 100, and there are infinite frequencies surrounding that, infinite frequencies, but very close values with the center frequency. Okay, 100, 100.5, 100.1, 100.2, like that. They're all continuous frequencies. Okay, they're not discrete ones. So that means there is no line spectrum. This is a continuous spectrum. So this is what you have all around that, but range is very small. So that is what is about the band pass filter, because first time, I mean, in this case, okay, all these things have come. I mean, so see, you should not confuse with this filter, because I am explaining in terms of, I mean, in terms of shapes I am explaining. In fact, this is the actual filter under consideration, low pass filter, and this is not the filter. Okay, this is cross correlation function, but the shape of this one appears like an impulse response of some system. So that system I am describing here, but actually this is not the system. This is the power spectral density of the given signal. This is the energy spectral density of the given signal. Okay, I should not even say that. I should not say that energy spectral density of cross correlation function. I should not say that. Okay, I should say that this is the energy. This is basically cross energy. This is energy spectral density of the input signal, and this is cross power spectral density of the input, both input and output. That is what I should say. I should not say that these are some energy spectral densities of the input autocorrelation function. I should not say. When I want to say in terms of autocorrelation function, I should say that this energy spectral density is the Fourier transform of this one. Okay, that's all. That much I can say. But I cannot say that the power spectral density. It is not power spectral density of this. Power spectral density of the actual signal. Okay, so that's very clear. And here, this is output. It is not signal. Output autocorrelation function. It is symmetric here. Unlike this, it is symmetric as expected. Okay, and this is the energy spectral density of the output. So these almost both are same, except for this rolling rate, because because so this point, 100 point is somewhere here at this point. So it is capturing only these things because of smaller bandwidth. Okay, this and this, when I multiply, what will happen? At this point, one point is multiplied with by 1. Other points are all multiplied with by 0.9, 0.8, 0.7, like that. Okay, so that is the reason I have that wherever I have got multiplication with 1, I have 1. All other things, this side and that side will come down. Okay, so this is actually the coverage is, if I take the width, the frequencies of the power, I mean energy spectrum width, that means where the significant energy is contained, that is between 0 and 200. This is the portion which is multiplied with this one, and effectively I got the similar rate, because these changes are very small compared to this one. Okay. Now high pass filter. So this is high pass filter, and this is very sharp. Is the sharp impulse kind of thing is there, and this is same thing. And here when you see, this is the stop band, this is stop band, this is pass band. Okay. Then what happens is, so these are the, let us say this is the, not GDP, this is the flat value, this is at what point, somewhere something like this here. Okay. So this is what, from here you will see this. Okay, because of course this is also included here. So from here onwards you will get some flat thing. So this is, whatever is there here, this is gone. This is not there here because you are multiplying it by 0. I mean 0 here. This is the 0. This is the stop band, 0. This 0 multiplied by this becomes 0 here. Okay. So this is similar spectrum because it's a high pass filter which is passing all the frequencies above this cutoff frequency. What you see is same spectrum you will see, but to the right of the cutoff frequency. Okay. So that is what exactly it is. Is not exact. From here it is taking, other portions it is removing. Now autocorrelation functions. So autocorrelation function is this, same thing, and cross correlation. Here it matters. There is a, from compared to the previous one, there must be some difference here. And YY. So okay, this is what low pass. Energy spectral density of output when passed through a low pass filter. Then when you pass this through a high pass filter, see the difference, how much difference, because it is passing all the higher frequencies. These are all higher frequencies are passed. Okay, there only lower frequencies are passed. So that is the difference here. Then band pass filter. When I take band pass filter, effectively you can say that, I will discuss first. Here, this is the signal convolved with this impulse response, and this impulse response is appearing like a band limited one, because I can clearly say, because the mean value of this is 0. If the mean value is 0 means it is not a low pass filter, and it is constant, it is almost constant frequency it is appearing, so it must be some kind of some center frequency here. That's why this shape you will get. So band pass filters impulse response will always look like this. It is almost sinusoidal if the bandwidth is less. If the bandwidth is more, again it is different. Okay, so it is different. So here when I convolve this, I am getting the output only at this point, that is between significant output between this and this. Why? Because between here and here, these are the frequencies, because this has in frequency domain here, it passes only certain frequencies. Those frequencies are present in this time slot. This is a time slot. Okay. Between here and here, frequency is changing linearly, but it is a time waveform. So during this period, the frequency is changing, and that change, whatever you wanted, so whatever I wanted means, what is that? This is the impulse response. This is the magnitude response of the filter, band pass filter. This is band pass filter. So what is the band here, bandwidth here? Let us take this something here, 3 dB, something 3 dB. So I can say that it is almost 40% or 30% of that one. So around 300 Hz, something like that. Okay. Approximately it is 300 Hz. Between 2 3 dB functions, approximately 300. 300 or even less than that. So this 300, this is the bandwidth. Okay, this is the starting frequency. What is starting frequency here? Bandwidth is 300, but starting frequency, I should say that at the first 3 dB point, it is 500 Hz, and at this point, it is 800 like that. Okay, so these are the frequencies. So I should say that this frequency at this point is corresponds to 300. This corresponds to 800. Bandwidth is 800 minus 500, that is 300. Okay, that is what it is. So basically, this filter passes all frequencies between 500 to 800. So here, when you see this chip is starting from 300. Initially, this is 300. At the end of the chip, I have 1200. So somewhere between, because this is 500 to 800, so probably it corresponds to this duration. Okay, so at this point, I have 800, and at this point, I have 500. So between these two time instants, the frequency changing from 500 to 800. So that these frequencies are passed. So during this, in time waveform, so between this only it is passed. Okay. Again, if you see here also frequencies are increasing. This is also FM waveform only, but whose envelope is modified. Whose envelope of the time waveform, here it was constant in the input. Here the envelope has changed. Okay, that is the only difference. Otherwise, these frequencies are same. Whatever frequencies here, they are transferred. These frequencies are transferred, and that's why you got this. Okay, and what about the frequency domain? You are multiplying these two. So this is your first. This is at 500. This is something like this. Something like this. This is something like this. And second one is 800 something like this here. So it is something like this. Okay. So basically, this portion is multiplied by this portion. This one is multiplied by this one. I will get this. I am getting this one. Okay. So these oscillations here, these oscillations, whatever I am seeing here, this side, they are because of this one. These are stretched because of the slope of this curve here. So these are stretched down like this because this is coming down, and this portion as it is, whatever portion is there, this portion is carried on to this one. Okay, so this is what I have. I mean, little bit fluctuations are there in my dry. So that is how this side, this portion, whatever is there, because that is within the bandwidth it has come. This is at the border basically. So it is almost in the transition region. These are all in the transition regions. So these are multiplied by these transitions. So this comes down. So effectively, the spectrum appears complex. It is not a simple shape, and accordingly, this spectrum is equivalent to this kind of signal. Okay. Now, if you see the autocorrelation function of this, is same. Energy spectral density. Now, cross spectral density, it is peaking at this point. So this is peaking at this point. So what I will get? This multiplied by this. Same thing is applicable in the spectrum, and even energy spectral density is also. This multiplied by this gives this. Okay. And this convolved with this gives this. Okay, this is a convolution relation this side, and there is a multiplication relation this side. Excuse me. So this, when you are multiplying, again only this portion, whatever in this portion is there, that is multiplied by this, it reflects into this. All other things, this side is zeros, this side is zeros. That is how you got that one. Then simulation 8 will go to band pass filter. I have shown for a single pulse previously with low pass filter and high pass filter. Now I am showing with band pass filter. So this is the band pass filter impulse response. Okay, and of course here the order I have changed. This is a different kind of filter here. It is not exactly whatever I have taken previously. It is a different thing. That's why you will see here this side transition region is different. This side it is closer. This side. Okay, so this is slightly different. That is the reason you will find these kind of differences between the accordingly. Okay, so this is a different filter. Whatever previously I have used band pass filter and this band pass filter are slightly different, and that because to demonstrate the outputs properly, I had to modify this impulse response. So this is the frequency response of the filter. This is the magnitude spectrum of the input signal, because a rectangular function, you remember very well, it is nothing but a sinc function like this. This is 40 milliseconds. Okay. So you have this these are all lobes, and it depends on this clarity, clear things. It depend on the number of points you have taken to represent the frequency spectrum also. Okay. So this is, then these two are multiplied. When they are multiplied, this is where we have multiplication here. So this is what you are multiplying. These two, when you multiply, you will get this one. Okay. So this is what you will get. Not much, you know already all other things I have already described in terms for low pass filter and high pass filter. Similar things are applicable here also. Then it is triangular function. I have a triangular corresponding energy spectral density single pulse, and the cross power spectral density again a bit complex, because this side slope is different, this side slope is different, even the profile is also different, this side and this side. And because of this asymmetry, when you multiply these two, you will get asymmetry in the output energy spectral density also. Okay. Then periodic signal I am showing. Again, band, say here same band pass filter again. Whatever I have shown here, this is the band pass filter I used here. This is the band pass impulse response. This is the band pass filter frequency response. Same filter I am using in this case also. Same filter. But it is a periodic waveform. So this signal is periodic, nothing change, and even here also it is same thing. Okay. Here actually you should get the line spectrum because of periodicity, but it is not dominant, because I could show it well there. Maybe this pulse width have changed a little bit. So because of that one, I am not able to show you here. Okay. I could demonstrate there for 20 millisecond pulse width properly. And autocorrelation function is periodic again. As I told you, this is because of the gating problem. And this corresponds to this energy spectral density. Okay. So this and this will multiply. You will get this. Okay, this should show some lines, but number of frequencies, because of number of frequencies probably they are not showing here. Number of discrete frequencies which I am taking. So, but shape is same. This multiplied by this, you will get this. Okay. Okay. So, thank you. Thank you very much for your attention. So, we will in the next class, probably we will go for an applications of cross correlation. Few applications of cross correlation probably we will see in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.